Okay, welcome back. And now we are starting the third lecture by Matt Hogancamp.
Okay, just a brief recap of the sorts of things we talked about yesterday. So we described how certain kinds of diagrams, like braid diagrams, correspond to some complexes of bimodules. There is, and then so if this is a diagram representing a braid, it corresponds to some complex of bimodules. There's a procedure, we can take such a diagram and then close it up, so connect the strands on the top and the bottom. This operation corresponds to what's called Hochschild homology of bimodules. A diagram with boundary will correspond to a complex of bimodules. The diagram obtained by connecting up the top and the bottom will correspond to just a complex of vector spaces. So just a normal complex by means of taking Hochschild homology. And this is a process that I won't define. I just want to say the sort of key word that we can talk about later, maybe after the fact, if you want to learn more about this. So the process of actually defining a complex for each braid is really this two-step process. Given a braid, you produce a complex of bimodules, and then closing up corresponds to computing some sort of invariant of bimodules. And then you'll get a complex. Even though this has the word homology in it, the result will still be a complex. You've only sort of partially taken homology at this point. And then the homology of that complex will be your invariant. And I say it's a complex of vector spaces, but I'm suppressing the fact that overall there's 3 gradings. One of those gradings comes from the fact that these are graded bimodules. A second grading comes from the fact that we've taken Hochschild homology. And then the third grading is the sort of remaining modular grading in the rest of the complex. Okay, so what I want to talk about today is the following sort of fun little graphical calculus. So the following is a sort of theorem I'll refer to a 2015 paper with me and Ben Elias. The complexes that I'm going to refer to, the complexes of bimodules that I'm going to refer to in this theorem were actually constructed earlier by me, but the application that we have in mind is from this paper, the later paper. So the theorem is that there exist some complexes of bimodules. I'll treat them as a black box for now. There exists some complexes of bimodules. I will call them Kn, and we'll denote them diagrammatically in this talk just by drawing an empty box with n strands. So we just invent a new diagram that represents K sub n, where this is n strands, with the following properties. So to fully understand or state the properties, we'll need a little bit more kind of language from the notion of homological algebra or DG algebra. But that's okay. We'll just sort of jump in and then I'll explain the things as we need them. So the first property the first property is that so complexes of bimodules have this composition operation given by tensor product of bimodules. So because we have, last time we discussed how a braid can be sort of converted into a complex of bimodules, this expression will make sense. So there's, you can consider this complex Kn composed with a braid on the top or on the bottom. And the statement is that this Kn absorbs all such crossings. Okay, so this is true for all i's, for which this makes sense, and it's also true on the if you put the braid on the bottom. So this thing eats crossings, so it acts as a sort of symmetrizer. You guys can maybe place this, in a similar, so you can interpret this thing as a certain, so it's a complex, you can think of it as a complex which is constructed from these bimodules that we associate to braids in some kind of complicated way. But it has this property that it eats braids, so it acts as some kind of symmetrizer. And what else? So there's a linear relation between, oh sorry, I guess I'm denoting this thing just as an empty box, so let me continue with that trend. So if I take a box on n strands, and then I wrap one more strand around it, so there's a linear relation, a quote-unquote linear relation between this term and the Kn plus 1 and the Kn with no wrapping. So there's a linear relation between these three terms, but here we're in the world of homological algebra, so the linear relation is, there's different ways of expressing the fact that you have a relation between three complexes. You can use the language of triangulated categories, so I can talk about a distinguished triangle between these three complexes, or we can use the language of like traditional homological algebra and say that there's a long exact sequence in homology, blah, blah, blah. I'll prefer the following way of expressing that there's a linear relation. I'll say that this complex is homotypically equivalent to something like of this form. And there needs to be some grading shifts here, so this is a q squared, and then there's an overall grading shift of t to the 2n q to the minus 2n, where this is n strands.
When you draw this extra strand, so what does it correspond to algebraically? So stacking vertically, I understand it's tensor product of bimodules, but stacking horizontally?
Yeah, great question. So if you have two diagrams, placing side by side is an operation that we call external tensor product. And all it is it's coming from the following fact. So everything in sight is a bimodule over some polynomial ring, Rn. So a diagram on n strands will be a bimodule, correspond to a bimodule over Rn. And you'll notice that Rn tensored with Rm over K, well, you can think of this as being, this has variables x1 up to xn. This one has variables x1 up to xm, but let me relabel and call them xn plus 1 up to xn plus m. So the tensor product of Rn and Rm is in fact isomorphic to Rn plus m. And so the placing bimodules side by side is really just tensoring over K, and then utilizing this isomorphism. So you have a kind of a right action or a bottom action of Rn tensor Rm, and you have a top action of Rn plus F. So that's what placing side by side does. Okay. And this notation I'm using to mean the following. So in order to interpret what's being said here, so I'm not quite finished with the statement of the theorem, but let me pause for a moment just to explain what this notation means. In general, there's a notion of twisting. So if X is a chain complex, then we can consider complexes which have the same underlying chain, suppose X is a chain complex. So we have the underlying graded vector space, called V, together with a differential. Suppose we have another chain complex, Y, which has the same underlying chain groups, so the same V, but a different differential. Then we'll say that Y is obtained from X by twisting, and we're going to write this. So the notation that we use is Y is a twist of X, and then the term that is added to the differential of X to get Y is written as a subscript. So this is notation. And the system of equations d squared equals 0 and d plus alpha squared is 0 is equivalent to the system of equations d squared is 0 and alpha satisfies a Marr-Cartan equation. So any element alpha satisfying this Marr-Cartan equation can be added to the differential of X. And so the kinds of twists of X are parameterized by Marr-Cartan elements. Anyway, so that's notation. There's particular kinds of twists which are especially nice, called one-sided twists. And so if you have a pair of complexes x1 and x2, then you can consider twists which are, so an endomorphism of a direct sum is given by a 2x2 matrix. And you can consider twists which are lower triangular with respect to the direct sum decomposition. So if alpha is of the form strictly lower triangular, then any twist, so if we take a direct sum of complexes and twist by a lower triangular, then this is called a one-sided twist. We define that notion to be one-sided, and we denote it. This is non-traditional, non-standard notation, but I find it very useful. We're going to denote a one-sided twist just by writing direct sum tilde. So we write direct sum tilde if to denote any complex which is obtained as a one-sided twist of x1 and x2. And the notion of being a one-sided twist is in fact associative. If you're a one-sided twist of, so if x1 is a one-sided twist of two other complexes, then so you have a certain kind of associativity. So like if you have a one-sided twist of complexes x1 and x2, where the twist goes from x1 to x2, and then another one-sided twist is built up out of that pair of things and a third, well then this is isomorphic to a one-sided twist. In this way, again, assuming all the differentials kind of increase the index, this will be equivalent to a one-sided twist in this fashion. And so this associativity means we can just write anyway, and this notation here, really, I just want to write it as one-sided twist.
But so what you call on one-sided twist is more or less a mapping cone, or?
Yeah. So great. So the one-sided twist that I'm referring to is the analogy is one-sided twist is like addition, and mapping cone is like subtraction. Mapping cone isn't associative. It's associative once you remember the shifts that are involved. So the actual cone, if you have a chain map from x1 to x2, then the mapping cone of this chain map it's literally, you have to shift x1, and then it's a twist of this sort. Mm-hmm. But it's not associative because of the shift that you have to insert. It is mapping cone, but there's a hidden shift that occurs, and so I want to not have any hidden shifts so that I can actually like reassociate without having to worry about.
Yeah. So you kind of you shift in advance, so to say.
Yes, I know. Yes, that's right. So. A general sort of one-sided twist could be expressed as an iterated cone. Okay. But anyway, so this is what this means. Oh, and then there's one more relation that we will need, which is, so we need to understand how these complexes, what happens when we take at the very last step where we want to close up, like we want to connect top and bottom and compute this Hochschild homology thing. So that's taken care of by the following local relation, which is, so if you have a kn plus 1 and you're closing up one of the strands either on the right or on the left, it doesn't matter, then this is an actual honest direct sum. Remember, closing up and taking homology will produce this triply graded chain complex. So you have Q's, T's, and A's. And this will be equivalent to A direct sum this shift to the n times just kn. And the thing that I want to point out right now is that every single chronological shift appearing on the board is even. This is why I don't like mapping cones, is because I want something which is manifestly has only even chronological shifts. And the mapping cone will obscure or hide that fact, because it will take something in degree 0 and shift it down into something that has. Anyway, so this manifestly only has even chronological shifts at all, or everywhere. So so the basic idea of how we're going to use this theorem is so this relation, when n is 0, this relation effectively allows us to take a strand and insert a k1 somewhere. So we start with a diagram that has no k's at all, and we produce a k using a relation of this flavor. And then by iterating this relation, we will produce complexes which either have a larger k and therefore absorb more bits of diagrams, or where k is in principle simpler because we attempt to simplify our diagram by applying relations of this sort. This one is in some sense simpler because we have a larger k which will eat more parts of the diagram. And this term is in principle similar, or potentially simpler because it has maybe fewer crossings. And so by iterating these relations, we may hope to compute, or we may hope to express our initial diagram as a twisted direct sum of terms with only even homological shifts and whose homology is like easy to compute.
Do you need to also normalize it somehow? Because so far you can take all these complexes to be zero and the theorem is true, right?
No, this, yeah, I see. There's a normalization which is coming from the n equals 0 case of this.
Okay.
The normalization is that K0 is well, it's a bimodule. In this degenerate situation, K0 is just the ground field.
Okay, that's already there.
And that's non-trivial because this gives, so the n equals 0 version, let's give these relations names. So this will be relation 1, this will be relation 2, and this will be relation 3. And so relation 2, when n equals 0, gives us the statement that a single strand is homotopy equivalent to a twisted direct sum where we have a K1 mapping into K, mapping into this guy. And so what's actually happening here, we can be kind of explicit. So the bimodule occurring here, this is the identity bimodule with one strand. And so this is simply the bimodule that has, it's the identity bimodule of this ring. Mm-hmm. And we're saying that this is homotopy equivalent to a shift of itself plus, maybe with some differential or some whatever, plus something. And the K1 in this case, yeah, let me just tell you, tell you a few things. So K0, as we said already, is just the ground ring. K1 is the cone, and maybe I'll prefer this notation. So it's the mapping cone of multiplication by x1. And so you have to shift this one in homological degree and shift this one in Q degree. And so that's K1. And what this homotopy equivalence is expressing is the fact that you can rotate this triangle. So you have a kind of projection map. You have a projection map which is homological degree 1 onto the trivial bimodule. And this sort of twisted direct sum involving those two terms. These two terms will cancel and you recover the trivial bimodule. So this equation is expressing the fact that polynomial ring looks like something one-dimensional. So the polynomial ring is expressed as something which is like quasi-isomorphic to just K, x1 mod x1, plus the rest. And it's not literally a direct sum, it's a sort of extension, and which is why there's a twisted direct sum. So the moral of what's going on here is something something similar to this. And in general, these Ks are kind of complicated to express, but all we need from them is what's written on the board. There's one more fact which is going to be used implicitly everywhere, which is that if you have a twisted direct sum, or a one-sided twisted direct sum, then you can modify the summands up to homotopy equivalence, and that will not. So modifying the summands is a valid operation. So this is called homological perturbation. Lemma or theorem, I don't know. This is a lemma. So if I is a partially ordered set, and we have a finite partially ordered set, and we have a twisted direct sum which is indexed by I, well, if each xi is homotopy equivalent to some other complex yi, then we can modify each summand in this twisted direct sum by replacing it with the thing that's equivalent to. And homological perturbation tells us exactly how to modify the Maurer-Cartan element acting on this thing in order to get a homotopy equivalent twisted direct sum on the right-hand side. So homological perturbation is the story of how to take a big iterated mapping cone or a big twisted direct sum and modify the terms up to homotopy equivalence. Okay? You should compare this to the theory of spectral sequences, which tells us how to relate the homology of a one-sided, which will tell us effectively how to relate the homology of a twisted direct sum with, so the theory of spectral sequence relates the homology of a twisted direct sum to the direct sum of the homologies. So replacing each xi by its homology doesn't give you an isomorphism here, but it gives you the second page of a spectral sequence converging to. Anyway, these are words that I don't need, because we don't need the theory of spectral sequences, because we use this homological perturbation lemma in lieu of spectral sequences. But there's a kind of a parallel story in which you could use the theory of spectral sequences, which here is actually a little bit weak. Well, it's both weaker and more powerful, because it applies to more general types of situations than merely twisted direct sums. But it's also weaker because you must take homology everywhere. So please ignore that. This is just sort of saying some words so they might excite some neurons. Okay. So this is and then maybe I'll just say in words, what is this twisted direct sum? In like usual topology, if you have a space if you have an actual space in a subspace, which is nice in some sense, like maybe it is a deformation retract of a neighborhood. So if A is a deformation retract of a neighborhood inside X, then you can consider like a short exact sequence of spaces. And then there's a sense in which the chain complex associated to X is a twisted direct sum of the guy associated to A and X mod A. So this is the same kind of thing that appears in this story as well. A cell or whatever, something in the chain complex for X could be thought of as a direct sum of something living in A and something living in the complement of A. And then the boundary map preserves A, but does not preserve X mod A. Anyway, whatever. If you needed more motivation for why twisted direct sums are...
Don't erase, please.
Oh, don't erase. Okay. Sorry, it's a weird habit. Okay.
This on the right you can. Sure.
So this is the strategy. So what we're going to do is we're going to start with a diagram for a braid beta. And essentially, without loss of generality, we're going to put a K1 somewhere. Because the identity, so essentially you choose a strand, and you can think of that strand as being something very, very like, that strand is basically like K1. Morally, you can think of it as something like this. But in reality, what it really is it's a twisted direct sum of K1 and a bunch of shifts of K1. Okay. This is actually a statement of causal duality, because it's like K1 twisted tensor product with the polynomial ring. The identity bimodule is like some kind of tensor product of this exterior algebra and this polynomial algebra. You should think of this as like an instance of causal duality. So anyway, so without loss of generality, you assume K1 is somewhere in your diagram. And then the strategy is to use relations 1, 2, and 3 to produce a big twisted direct sum of complexes with only even shifts, because every single one of those relations only will produce it'll produce a diagram with some even homological shift and some Q's and whatnot.
Sorry, can you just ask about what you just said about causal duality? Where is the exterior algebra a kind of misstep?
Yeah. So here is the exterior algebra. So this is, this is like,
exterior algebra will be taking quotient by square, not by x1.
sorry?
In the exterior algebra, you would take quotient by x1 square, not by x1. So I don't quite see the exterior algebra.
I mean, this is like causal duality internal to the category of bimodules. So instead of resolving the trivial vector space by, instead of resolving like the trivial vector space by some modules, in some sense, I want to resolve the trivial bimodule by some. So the exterior algebra is like, here is 1 times the identity bimodule, and here is theta times the identity bimodule. And what we're saying is that it's an instance of, so basically you take the exterior algebra in one variable theta times this identity bimodule. And that's what this is. Okay. I would be happy to talk more about that later.
Keep one moment for I need to make a copy.
Oh,
right?
Okay. So let's just see how this plays out on 2 strands, and then after lunch, I'll show you the really fun diagrams. How much time do I have, by the way?
You still have 10 minutes.
Okay. Okay. I think this was maybe not the... Since I have 10 minutes, the two-strand will not take too long. Let me just really iterate what I'm trying to say here. So the homotype equivalence that I have in mind when I write a statement like this is the identity bimodule on one strand can be expressed in the following way. And I really think of this as being like a categorified arithmetic in some sense. I don't know if this makes you guys happy or not, but so let me write one more. So we can consider a big complex. So there's actually only two homological degrees occurring in this diagram. So in homological degree 0, I see the direct sum of this and that and that and that and that. In homological degree -1, I will see the direct sum of this and that and that and that. Just on forever. And the differential, so the strictly vertical part of the differential is just multiplication by x1. And the other part of the differential is, let's say, minus the identity. Oh, sorry, that's not an x1, that's a minus identity. That's not an x1, that's a minus identity. So we can consider a complex of this form. And what I want to notice is that this can be written as this can be written as an iterated, as a twisted direct sum in the following way. So I haven't written the direct sum symbols, but it's implicit that you take the direct sum of every single one of these terms and then place a twist on it according to these arrows. Now, we can reassociate that big direct sum so it's like thought of as the direct sum of this term plus what I've circled in blue, plus what I've circled in blue, plus what I've circled in blue. Each one of these, and then so the arrows go from, notice the arrows go from this blue blob to that guy. So the arrows actually will, actually map us, I suppose, to the left here. So, okay. But each complex that I circled in blue is contractible. It's the mapping cone of the identity map, so it's a contractible thing. So each one of these are contractible, so they're homotopy equivalent to the 0 complex. And homological perturbation lemma, it does actually apply, so I've only stated it for finite posets, but it does apply for certain kinds of infinite posets. It applies as long as your poset is bounded from above, or like satisfies some kind of ascending chain condition. So this satisfies the ascending chain condition, because you can't continue indefinitely to the left, you'll eventually fall off the edge. So this is one of these situations where we can use some infinite version of HPL. So we can contract away all of the blue things, and we get and this is what I mean. So, but we could also reassociate, we can also reassociate not via the blue blobs, but via the yellow blobs. So if we associate according to the yellow blobs, then what do we see? Well, each yellow blob is K1 up to a shift. So we end up with the equivalence which says this guy is equivalent to K1 mapping into a shift of K1 mapping into a shift of K1 and so on. Okay, again, the homological shifts are all 0. In particular, they're all even. And this is my assertion that if we have no K1s anywhere in our picture, we can grab a strand somewhere, and that strand corresponds to this identity bimodule, and we can replace it up to homotopy equivalence by infinitely many copies of something with K1. And so without loss of generality, we just need to place a K1 somewhere and compute homology of that. And this reconstruction is quite easy to do. So if you can compute with K1, then you can compute without K1. Okay? And, okay. And this feels like causal duality. Like if you were to prove the causal duality between exterior and polynomial algebras, you would write down exactly the same picture. So I can make it more precise maybe another time. But let's just, with the remaining like 2 minutes, let me show you how to compute the Kavanagh-Rorzensky homology of torus, two-stranded torus knots with 0 effort. Like epsilon of effort. Okay. I'll be a little bit lazy with the degree shifts. The only thing that is essential is that they will be even, so that in the end our twisted direct sum our twist will be 0 for degree reasons. So we start with so if we take this diagram and close it up, so connect top and bottom, we'll get the 2-2 torus knot, torus link. Okay, so to compute the Kavanagh-Rorzensky homology of T22, we will close this thing up. So using relation 2 here, we can replace this with a larger K and an identity. And this one is easy, and this one is easy. So the homology of this one is computed by 2 applications of relation 3. How careful do you want me to be? Let's be really careful. So if we close up, this is a K2, and relation 3 tells me how to compute, I get an A and a T squared q to the negative 2 times this picture. Again, relation 3 applied here tells me that this is a q squared. This corresponds to the n equals 0 case of relation 3. So that's a direct sum 1. And in principle, there's some differential connecting this term to that term, but we'll see that that differential must be 0 in the end. Okay, so let's keep going. So this guy is the closure of a K1. So we get times the thing for K1. That is this term now. Twisted direct sum with whatever I get here. Now this is the unknot with no K1 on it, yeah? And so we've convinced ourselves that we can put a K1, we allow ourselves to put a K1 on that strand, but then the penalty for doing so is that we have to divide by 1 minus q squared. Where this, you have to be careful with how you interpret this. You have to interpret this in that way. So it's a direct sum of infinitely many copies of this thing with shifts, but then you compute that. Now you see something that has only even homological degrees. We see something of degree 0, 0, 0, 0, 0, 0, 0, and then a t squared. So in the end, we get a direct sum of just one-dimensional vector spaces, all situated in even cohomological degrees. So the differential must be 0. So this twisted direct sum is in fact an honest direct sum. The twist must be 0 for degree reasons. And then I'll let you use your imagination. What would you do if you had more? So if you had another 2 crossings, well, you would expand according to what we did in the beginning over here first. So twisted direct sum. And then you compose that on the bottom with a pair of crossings. Oops. And then you iterate. So this K2 absorbs those 2 crossings. So this is easy. And this is just the computation that we did already. So that's also done. And that's it. If you had an odd number of crossings instead of an even number of crossings, it sort of also works out. We'll talk about this after the break, but so on 2 strands, it's like quite easy. On more strands, it's a little bit more involved, but fun. So that's what we'll do after the break. Thanks, guys.
Questions? Okay, so let's thank Matt again.